So let's see what the transpose of a matrix is, what transposition is. Um, Transpose of a matrix is a matrix made where you replace the rows of the original matrix with the columns. So like you see that if I have a 2 by 2 matrix with the first row equal to 6 and 2, the transpose of this matrix would have its first column as the first row of the original matrix, and the second row would go to the second column. Or you can do it the other way around, like you would see that the first column of the original matrix would be the first row of the transpose version. The second column would become the second row. Um, if a matrix has m rows and n columns, the transpose of that would be having n rows and m columns. And every element of the original matrix, if has index I and j, in the transpose version would have indices j and I. So you see here we have a matrix with 3 rows and 2 columns. If we transpose this, we would have a matrix which has 2 rows and 3 columns. Each row of the first matrix would be the columns of the transpose version, or each column of the first matrix would be the row of the would be appearing as rows of the transpose version. Um, if the transpose of a matrix is equal to the original matrix, we call that matrix symmetric. Okay, so this can only happen for square matrices. So you can see that for a square matrices, nothing is gonna happen on the main diagonal, but the non-diagonal elements would get mirrored with respect to the main diagonal. So you see that 2 was here, 1 was here in the excuse me, in the transpose version. The place of 1 and 2 are swapped. For symmetric matrices, basically you would see symmetry with respect to the main diagonal. Some properties of transposition are explained here. If you do transposition twice, you would get to the original matrix. So A transpose transpose is going to be equal to A. A multiplied by B transpose, this is matrix operation. It's going to be equal to B transpose multiplied by A transpose. So the order is going to be changed. And A plus B transpose is A transpose plus B transpose. These are very easy to prove. We're not gonna do that here. This is the same for subtraction as well. So A minus B transpose is A transpose minus B transpose. How to do transposition in MATLAB. So if we have a matrix which has all of its elements as real numbers, there's no worry, like we can either use the single quote operator or the dot quote operator. Both of them would have the same results. So let's just like see that in MATLAB. Let me see, I already have something. So let's just like go to this one, A equal to this, and A transpose. You see that the original matrix had 2 rows, 3 columns. The transpose version would have 3 rows, 2 columns. And A dot single quote would be exactly the same. However, in MATLAB, if you have a matrix which has complex numbers in any of its elements, then the quote operator and the dot quote operator would behave differently. The quote operator would not only transpose the matrix but also conjugates all the elements. And you remember what the conjugate of a complex number is? The conjugate of a complex number is where you negate the imaginary part. So you basically mirror the imaginary part, mirror the complex number with respect to the real axis. So for example, 2 plus 3j, if you take the conjugate up, if the conjugate of 2 plus 3 I or 2 plus 3j would be 2 minus 3j or 3i. Let's see that in MATLAB. So let's just like have another matrix. So here you see that here we have a matrix which has some of its elements as complex numbers, most of its elements as complex numbers. If I do a quote operator, well, you see that it transposed the matrix, but in addition to that, it also changed the elements. So here, like we had 1 plus 1i, but here we have 1 minus 1i. Here we had 2 minus 3i. Here we have 2 plus 3i. So the quote operator, the single quote operator, not only transposed the matrix, but also conjugates all the elements. Right? And then a dot quote operator, it's just going to transpose the matrix. Okay, so like if you have a matrix which has complex elements and you only want to transpose it, you have to use the dot quote operator. To conjugate a complex number, you remember that conj is the function that conjugates a complex number. Just like put multiplication here. It's taking time. Yeah, so this is the function that you can use to conjugate a complex number. Anyways, let's continue. So now we get to the concept of linear independence of vectors. A set of vectors is linearly dependent if at least one of the vectors can be expressed as a linear combination of the other vectors. So basically, if you can make one of the vectors out of the other two vectors or the other like n minus 1 vectors, that set of vectors is called linearly dependent. It means that one of the vectors, at least one of the vectors, depends on the other two. So one of them basically doesn't provide any new information. You can make them out of the other two. Let's look at these three vectors. Do you think we can make one of them out of the other two as a linear combination of the other two? So let's call this one A, this one B, this one C. Let's look at C. Can I make C out of A and B? Yes, I can. If I multiply A by 2 and just add it with B, I get C. So 2A plus B would be equal to C. That's a linear combination of A and B. So this set of vectors is called linearly dependent. A set of vectors is linearly independent if none of the vectors can be expressed as a linear combination of the other vectors. So an example of that is given here. So this set of vectors, these three vectors, you can't make any of them out of the others. So you can't express any of these vectors as a linear combination of the other two. You see that here, like if I wanna basically make this one, I have to multiply this one by 1 over 2, but that is gonna cause problem for this element. The same thing for the other vectors. We're gonna see how to prove that a set of vectors is linearly independent or linearly dependent a little bit later, but like we just want to know what the concept of linear independence is. Linear independence means that you have a set of vectors that none of them can be expressed as a linear combination of the others. Okay, so it means that they are independent. The term linear comes from the concept that like you can't make them out of linear combination of the other vectors. Okay, so basically each of these vectors, they provide some unique information that the other vectors cannot provide. Okay, so that's the concept of linear independence of vectors. A rank of a matrix is the number of linearly independent columns of the matrix. So I put the same three vectors that we had in the previous page here in a matrix. So each of these columns, you can think of it as a vector, right? And we saw that only two of them are independent. The other one can be made out of these two. I can't make this one out of this one. I can't make this one out of this one. But I can make the third column out of the first two columns. So the rank of this matrix is 2. However, for the other matrix, the 3 columns are 3 independent or 3 linearly independent vectors. So the rank of this matrix is 3. We mentioned that the rank of a matrix is the number of linearly independent columns, but also the rank of a matrix can be found as the number of linearly independent rows of the matrix. So you can look at the columns or you can look at the rows. Now, if you look at the rows of this matrix, you would see that easily, like I can make this one out of linear combination of these two. How? I multiply the first one by 0 and multiply the second one by 0. Now I can find the third and add them together and I find the third row. Okay, so from this example you can find that if you have a 0 vector in a set of vectors, that set is definitely linearly dependent. Okay, so that's something that you can get from this example. But however, like for the other one, even if you look at the rows, there's no way that you can make one of these rows out of linear combination of the other two. You can try that, you can just like, but it's not going to be possible. Okay, so rank of a matrix again is either you can find it as the number of linearly independent columns of the matrix or the number of linearly independent rows of the matrix. In MATLAB, you can find the rank of a matrix using the function rank. So let me let's just go to the original A that we had this one. If I say rank of A, can the rank of this matrix be 3 or 4? No, because we only have 2 rows. So the rank of this matrix is definitely either 1 or 2. Okay, so here we see that like the rank of this matrix is 2. It can't be 3 because we only have 2 rows. Okay, so from this definition you can know that the rank of a matrix is always smaller than or equal to the minimum of rows, number of rows and number of columns. Okay, so like if you have a matrix which is size m by n, the rank of that matrix is definitely going to be smaller than the minimum of m and n. Now let's talk more about singular matrices. We already saw that a singular matrix is a matrix that's not invertible, or it's not, or its determinant is equal to determinant is determinant is equal to 0. Now we have like some equivalent statements here. We say that a square matrix is singular if any of these conditions is satisfied. If any of them is satisfied, it means that the others are also satisfied. Okay, so we already saw that a matrix is singular if its determinant is equal to 0. Well, if its determinant is equal to 0, it means that it's not invertible. If that's the case, it also means that the columns of this matrix are linearly dependent. So they're not independent, they're dependent. And the rows are also linearly dependent. And we say that the rank of the matrix is smaller than n. Okay, if the rank of a matrix is equal to n, we call it, for a square matrix, we call it a full rank. For a singular matrix, it's not a full rank matrix. Its rank is definitely smaller than n, the number of rows and the number of columns. All of these conditions, all of these statements are equivalent. So if you want to prove that a matrix is singular, you can use any of these conditions to prove that the matrix is singular. You can find its rank, you can find its determinant, you can see if you can invert it. You can look at the columns and find if they're linearly independent or not. You can look at the rows, and that's what a singular matrix is. There are some special matrices that we are gonna see in this lecture. So let's see, like we already saw, like what a diagonal matrix is. A diagonal matrix is where all the non-diagonal elements are equal to 0. Okay, all the non-diagonal elements are equal to 0. We call that matrix diagonal. Right? A, B, and C are also, they can be 0 as well. So like we don't care about the diagonal, we only care about the non-diagonal elements. If the non-diagonal elements are equal to 0, we call that matrix diagonal. A matrix is called upper triangular if all the elements below the main diagonal are equal to 0. This is an upper triangular matrix, right? It means that only the upper triangle elements are non-zero, right? Like everything else is gonna be 0. Again, sorry, like I have to correct myself. So like we only, like for like having an upper triangular matrix, we only say that like the elements below the main diagonal should be 0. We don't know like what A, B, C, D, E, and F are. They can be also 0. A matrix is lower triangular if all the elements above the main diagonal are 0. The identity matrix is a special version of the diagonal matrix where all the non-diagonal elements are 0 and all the elements on the diagonal are equal to 1. That's the identity matrix. We're already familiar with this. A tri-diagonal matrix is a matrix which has elements on the main diagonal. If we exclude the elements on the main diagonal and the sub-diagonal above and below that, if we exclude that, all the other elements are going to be equal to 0. You see that like we have one main row and two one main diagonal and two sub-diagonals. If we exclude these three diagonals and sub-diagonals, all the other elements are equal to 0. We call this matrix tri-diagonal. Again, we don't care like what the rest of the elements are. If these elements are equal to 0, we call this matrix tri-diagonal. So we already saw how we can express a system of linear equations into a matrix equation. One of the methods to solve a system of linear equations is Gaussian elimination. So first you convert that system of equations into a matrix equation. Then what you try to do is try to do some operations on the rows so that the coefficient matrix becomes either upper triangular or lower triangular. So here I'm not gonna spend too much time like proving this method, but because you've already seen this in your linear algebra course, or you will see that later. But here we want to see that we have a system of equations, right? If we want to solve this, we can change each of these equations based on the other two as a linear combination of the other two equations. Still, we will get the same results. Okay, so that's something that we should know. So what we try to do first, we try to make these numbers below the main diagonal on the first column. We try to make them 0 using the diagonal elements. So if I multiply the first row by 2 and add it to the third row, this would become 0. If I multiply the first row by -2 and add it to the second row, this coefficient would also become 0. But you have to be careful that whatever operation you do for the matrix of coefficients, you have to do it on the right hand side as well. So you see that the right hand side vector is also changing. Okay, so like we achieved like the first step. So like we made all these coefficients equal to 0. However, this matrix is not still upper triangular. So what we can do here to make this other element equal to 0, we can multiply the second row. So we use this number on the main diagonal as the pivot. So we multiply this second row by -4 and add it to the third row, and then we end up with this matrix equation. So from this point, if you look at the third equation, it's very simple. You would see that like it's equal to -4 times b3 equal to -4. Now we know that b3 has to be equal to 1. So now that we know the value of b3, we can now look at the second row. So the second row tells us that b2, 1 times b2, 0 times b1, so 0, plus 1 times b2 plus 2 times b3 has to be equal to 0. So by back substitution, we already know the value of b3, which is equal to 1. So b2 plus 2 has to be equal to 0. So it means that b2 has to be equal to -2. And then again, by back substitution, if we look at the first row, we already know the value of b2, we already know the value of b3, we can find the value of b1 from the first equation. This is called the Gaussian elimination. So you try to simplify equations so that like you have only one element left in the one unknown left in your equation, and then you can easily back substitute it in the previous equations and find all your unknowns. One of the problems that we already talked about this. So like in this step, the second coefficient in the second equation was the pivot. So like sorry, let me go back. So first, in order to make these two 0, this number on the main diagonal was the pivot, and then 1 was pivot to make this one 0. So this is explained here. In MATLAB, if you want to solve a system of equations, a matrix equation, you can, and you want to use the Gaussian elimination to do that, you can use the backward slash operator, or called left division operator, or you can use the ML divide function. So actually, let's see. I'm just gonna write this down: 2, 4, -4, 1, 3, 2, 1, 4, 2, and 1, 2, -6. If go to MATLAB and just like have a equal to 2, 1, 1, 4, 3, 4, and -4, 2, and 2. Let's have b also defined here. B is equal to 1, 2, -6. So if I say A left division B, MATLAB would find the vector of unknowns for us, and the way this is implemented is using Gaussian elimination. So like you already saw that B3 was 1 and B2 was -2 and B1 is equal to 1, or you can use the ML divide function and say like A comma B. You would do the same thing, exactly the same thing. One of the problems that might arise when you apply Gaussian elimination is that you might end up with a 0 on the main diagonal. So then it's not possible to use this number as the pivot to make the lower triangle elements equal to 0. So one way to combat this is to determine the coefficient with the largest absolute value in the column below the pivot element, and then you just like switch the rows so that the 0 would be not on the main diagonal. This is called partial pivoting. This is already implemented, so like this is only for your information. So if you want to implement partial pivoting yourself, you can write your own function that does it. So for example, this MATLAB code that's displayed here, this is implementing the Gaussian elimination using partial pivoting. So you see that if we have zeros on the main diagonal, we have to substitute the rows. So partial pivoting happens here. We find the maximum element on the, as mentioned here, we find the largest absolute value in the column below the pivot elements, and we do swapping of the rows. This is only for partial pivoting. Otherwise, like what you just need to do, you just have to multiply, or like divide, let's say like multiply. Let's like multiply this this row by the number, by the proper coefficient, and then add it to the other row that you want to make the element equal to 0 to make this one 0. So we saw that here we multiplied this by -4 and added it to the third row. You can think of it as division as well. So like what we do, we just basically divide all the elements of here by 1/4. That's what's happening here, which is the ratio between the pivot and the element that you want to make 0. The negative of that. Now, Gaussian elimination is a seems to be a very straightforward approach. However, there are some conditions under which the algorithm would break down. So the most common problem happens when one of the pivots is found to be 0, and if this is the case, and like we saw that we can do partial pivoting, but sometimes it's not possible to do that. An example of that, which happens for singular matrices, is shown here. So here, for this matrix equation, we applied Gaussian elimination, and this is what happened. So like here, this element is 0, but also the element below that is equal to 0. Now let's look at this one. Let's look at this system of equation. So in this case, the third row would tells us that B3 has to be equal to -2, because it says like 0 times B1, which is 0, plus 0 times B2, which is 0, minus 2B3 has to be equal to 4. So it means that B3 has to be equal to -2. But the second row would tells us that 3 times B3 has to be equal to 1. So this is contradiction. B3 cannot be both -2 and 1/3 at the same time. So this means that this system of equation has no solution. If we look at this matrix, can you tell me if this matrix is singular or not singular? Right, so one way of answering that question is to find the determinant of this matrix, but that's a little bit too much for us. The other way is, like, you remember that there were some equivalent statements that we can check. There's some equivalent requirements. One of those statements or requirements were that are the columns of this matrix linearly independent. Let's look at the first column and the second column. Can I make this column out of the other columns? Yes, I can. If I just multiply this one by 2, it's going to give me the second column. So 2 times the first column plus 0 times the third column would give me the second column. So you see that when you have a singular matrix, if you apply Gaussian elimination, this is one of the cases that might happen. This shows that the system has no solution. Now, I didn't change the coefficient matrix, but I changed the right-hand side vector. So again, we apply the Gaussian elimination, and we end up with the same matrix on the left side. Now, look at this one now. The third row would tells us that B3 has to be equal to -2. The second row would tell us the same thing. So we know that B3 is equal to -2, right? What does the first row tells us? Oh, what does the first row tell us? It tells us that B1 plus 2B2 plus B3, which we already know what it is, has to be equal to 1. So if we simplify that, it basically tells us that B1 plus 2B2 has to be equal to 3. How many pairs of B1s and B2 can we find that satisfies this equation? Infinite pairs, right? I can choose any value for B1 and find the corresponding B2. B1 can be 0 and B2 would be 1.5. B1 can be 1, B2 would be 1. B1 can be 3, B2 would be 0. B1 can be 1.5 and B2 is going to be 1/4. And, or sorry, no, B1, if it's B1 is 1/5, then B2 is going to be 0.75. Or 3/4. So this basically tells us that if a matrix is singular, if the coefficient matrix is singular, we might have two different cases. Either our system of linear equation has no solution, as an example, this one has no solution, or it's gonna have infinite number of solutions. Okay. if the coefficient matrix is not singular, which was the case here, for a square matrix, for like when the number of unknowns is equal to the number of equations, our system is gonna have a unique solution as we found it, okay, using the Gaussian elimination method. Now let's look at another concept, a span of a vector space. If all vectors in a vector space can be expressed as a linear combination of a set of vectors, let's say like these k vectors, then we say that these set of vectors v1 to vk, they span that space. So as an example, here look at these three vectors in the three-dimensional space. Okay, if we have these three vectors, any other vector in the three-dimensional space can be expressed as a linear combination of these three vectors. Okay, so you can think of any vector in this space, and you can make that vector, or you can express that vector as a linear combination of these three. So we say that these three vectors, they span this three-dimensional space. This is not a unique set of vectors. You can find other three vectors that would span the same space. Okay, and we'll see that for a set of vectors to span a space, they have to be independent. For the minimal set of vectors to span a space, they have to be linearly independent, which is the case for these three vectors. You can't make any of these as a linear combination of them. The cardinality of this set is the dimension of the vector space. So here, because we need three vectors to span the whole space, the dimension of this space is 3. If we didn't have the third dimension, we only needed 2 linearly independent vectors to span the whole space. And for a space, we have another concept called basis. A basis is a set of maximal set of linearly independent vectors and a minimal set of spanning vectors of a vector space. So here you would see that here we have 3 linearly independent vectors, right? And this is just we can also add more vectors here, but we don't need them. We only need 3, so that's why it says minimum here. And sorry, that's why it says maximum here. And then they span the whole space, only the three-dimensional space, right? So this is what the base. So we can call this we can choose this as these three vectors as a basis of this three-dimensional space, which is what we do in math and physics and algebra. You know that this is called, you usually call this one I, J, or K, and we can express any point or any vector in this space as a linear combination of these three vectors. But this set of bases is not unique. Any other 3 linearly independent vectors in the three-dimensional space can be chosen as the basis for that space. But in the Cartesian coordinate system, we use these 3 vectors as the basis. So that's what a span of a vector space is. Let's just